Sorry about that. Okay, so we're recording and we have your contract here. So I've made no changes here. This is basically the one that you had sent me.
Okay.
So yeah, advertise deposits.
I can't see your screen yet.
Oh, whoops. Yeah.
Thank you.
Cool. Okay. Thank you. Yeah. Always tell me, because otherwise it's okay. So advertiser deposits, that's fine. And then the member votes, and they choose either 1 and 2. So far so good. But now there's this strange thing, which is basically if the member made the choice non-profit 1, which is not quite right, because non-profit 1 is not the name, not the value of the choice. They're choosing the value 1 or 2. I imagine you intend for 1 to correspond to non-profit 1 and 2.
Yeah, and you're 100%. You're 100% right. So my, that makes it clearer for me. But that is the intention for just like understanding what the choice means.
Yeah. So let's have a look at how we would do that, because I don't think it's.
So really, like you were saying, nonprofit 1 just means choice 1.
Yeah, choice 1. Yeah, that's right. So I think what we want actually is this guy here. Value is equal to, and the actual value will be the choice by member. And that should be equal to value 1.
Nice.
So that's not too bad. That's just this thing that we can replace. Now, a really good question is, what does this mean? What's this observation mean?
So the point was someone would visit the We Think It Matters campaign.
Yeah.
It could be any member, and they would be choosing between one of the 2 nonprofits presented.
Yes. No. I completely understand what you intended. And I think the way to do that is this thing here.
And that makes sense.
But I'm just wondering what this observation, like what this option even means, because all of the others make sense, like and, or, not, value equals, those are all values. But then this is like whether the party made a choice. And I guess that thing would always be false here, because non-profit 1 doesn't exist as a choice. But say if we had you know what I mean?
I see what you're saying. You're talking about the party block.
Yeah, what's that actually talking about? And I mean, I'm assuming that this is asking, has this party made this choice? But
I see what you mean. Like how they best mean to use it.
Yeah. Like it's sure, it's a thing to ask, but I don't know when you'd use it, because obviously the party's made the choice when you force them to make a choice up above, right? Up above here. So I don't know. It's weird, but I'm just gonna, pretend that doesn't exist for now. And then I'll duplicate this and I'll move the same reasoning to.
Yep.
Yeah. So, very good. Like basically, I think with the exception of that part, I think this contract.
Don't forget to change the Yeah.
Yep. Thank you. Okay, so basically, if we choose 1, then we pay nonprofit 1 5, lottery 1 1, lottery 2 1, and we think it matters 3. Cool. And in this case, we pay nonprofit 2 5, lottery 1 1, lottery 2 2, and we think it matters. Cool. So one thing we can do in the Haskell maybe is like this whole section is the same in both branches, we can pull that out. Maybe. Yeah, probably. And then yeah, we pay nonprofit to this. And I guess what you want to do ultimately is allow any number of not members, any number. Wait.
Well, yeah, is the right word recursive?
Yeah.
Yeah, recursive until the amount that was deposited by the advertiser runs out.
Okay. Cool. So that means, so it's still the same two members. Sorry, it's the same member voting over and over again, or you want multiple members voting?
Yeah, no, multiple members voting until the initially deposited funding is gone.
Okay, cool. That's going to be like there are a few. So one thing is that each vote spends, we know how much money each vote spends, right?
Yep.
It may go to nonprofit 1 or 2, but basically it always spends 5, 6, 7, 10. Okay, so that's cool. That means that we can kind of create a static contract, because like what would be more difficult is trying to dynamically decide in the contract of how much money is left. But I think in the case that you described, we can do it until the money runs out and generate a whole contract for that. So that's perfect. Okay, so let's.
Yeah, and just to be clear too, so you know that constant that they deposited in this case would mean that this is a 10,000 vote campaign. So 10,000 different members need to pick nonprofit 1 or nonprofit 2.
Cool. Okay, cool. So what we're gonna, so presumably,
or until that certain epoch when the campaign's over. So either of those two things could happen. They could hit the maximum of the constant deposited, or the time of the campaign could run out.
Right. Okay, cool. That's good. Okay, let's there's a few bits to do. What's this complaining about? Oh. Let's go back to Blockly, because something's wrong. When value is equal to choice ID name role member. Okay. Oh, I see. Choice has to be vote in both places.
Nice.
Yeah. Okay, that's better. Okay, so let's copy it into Haskell.
I understand those changes you make too. It makes a lot more sense.
Yeah. I as soon as I looked at it, it looked a little bit off, but like I understood exactly what you were trying to do, and I think that what's puzzling me is not so much sure we changed that condition, but when would you use that other type of condition? And I don't see it right away. That doesn't mean it's not there. It just means I don't see it. Okay, so let's paste this updated contract up here. And we've got a few things to do. So let's do a little refactor first, just little things just to make it a little bit more readable. Changing everything that says this. Okay, so
you got one more under the pay right above it.
Yeah, cool. So the next thing I want to do is like, how do we, I might have to, let me just compile again and see if I can open Blockly in a new tab so we can kind of Maybe not. Yeah, so one thing I want to do really is make a function out of this part, because it's the same thing. The only thing is we pay non-profit 1 sometimes and non-profit 2. The rest is all the same. So yeah, let's get us back to Haskell and do that. So I'll call it single round payout, right? And that'll be a contract. Like, so that's, but it'll specifically take the name of the nonprofit and return you a contract, right? Because that way we can do the two. So I know it's not going to be a string, but I think it's going to be a token name, but I'll just write string just to have the compiler tell me what the type is supposed to be.
Gotcha.
So single round payout, and it'll take a winner equals, and then it's going to be that, this whole part. I wish you would highlight the, so yeah. So basically it's going to be that, and it's going to pay winner here. So I presume that's going to complain about that string type, because it's going to be a, let's see. Yeah, couldn't match type char. Remember char list like this, that's a string, and it wants a ledger value token name. It's my biggest criticism of this kind of Marlowe library here is that it's using something called a token name for a role, because it's, you know, it's not a token name. It's a role name. But
makes sense.
Yeah, and that should be ledger value. Okay, so we have to import ledger.value token name, and we'll say token name here.
Yeah, it doesn't. Then that name doesn't really match the use case.
Yeah, and look, I appreciate it that it's just their own internal string. How it's just a string under the some kind of string. It could be a text or a string, but I really don't want to get into Haskell string problems and why there are multiple types of strings. But yeah, so they've used, it's kind of the same thing, but I think good typed functional programming, which they seem to do in general, would need you to use different types here. So, because I mean, the problem is that you are, as we stand, you're able to pass a token name where you expect a role name, and role name where you expect a token name, which has potential for bugs, and you could avoid that with types. So in my opinion, they should be different, but it's okay. It's not a big deal. Cool. Okay, so we've done that single round payout. And let's just do it here for nonprofit 1 as well. And let me just line up the brackets. It's, yeah. And yeah, we're going to need some brackets here just so it's. So what's it complaining about here? Let me just try and compile it again to see what. I feel like we've still got something wrong. No, we don't. Okay, we're good. Cool. So that should be the same. It's just that we've kind of done that part. And what I'll do next is I'll pull out this function, this whole when with the votes, And
That's the reclusive part, right?
recursive. Yeah.
Recursive. Yeah, thank you.
Yeah. So yeah, because what it's going to do is take a list of members and do each one basically. So let's see. So there we're going to match to there. Yes, that's right, because that's the case. Okay, so basically I will call it voting. I guess I'll call it voting round for now, but then you'll see it'll end up being called voting rounds. But yeah, I try to always, when I'm refactoring, especially when something's a little bit complicated, then I try to either refactor or change functionality, but not both at the same time. So for example, here, when I'm just pulling this into a function that's not changing any behavior, making it recursive obviously is changing behavior. So I like to do that in 2 steps rather than 1, even if so
makes catching little mistakes a lot easier.
Yeah, it just helps you focus your mind, because I mean, like, programming is basically, the reason programming is hard is because our minds are kind of not made to focus on this kind of detail with this kind of complexity all the time. And that's what's hard about it. Like, the actual parts are not hard, but like just kind of managing complexity is, which is why I kind of like to really just simplify things for my own brain. Okay.
Makes sense.
So voting round is a contract, and that. Guess we don't need those outer brackets. And here, I think it went here. Yeah, it would have. Cool. So if we compile that. Okay. So that's so far so good. Now, what we want to do is, for this voting round, we want to take the member that voted, basically, because just step by step. So instead of just always having member, we'll have a member name. So that's, now we know it's a token name, so I'll just say token name straight away, but it's actually a member name.
And that would be each unique voting member.
Yes, yes, correct. So that's going to be member name there, and member name there. And I think that's it. And there. So member name votes, and then when his or her vote ID is vote is 1, then we pay nonprofit 1. Else, if their vote is 2, then we pay nonprofit 2. And else we close. So yeah, that's fine. Cool. I'm just looking at whether we're missing anything.
Well, you've already taken out the other parts.
No, it's fine. Yeah, that's right. So we got an if, and then this is actually an else if. Yeah, so I think we're fine. So all we have to do now is, for voting round in the contract, voting round has to take member. Like that. So should still be all good, I hope. Okay, cool. So far so good. Now what we want to do is, well, there's 2 ways we could do it, right? and this is where kind of you start having these design decisions where, so instead of taking a single name for this voting round, oh, sorry, I've got a plane going overhead. It'll pass in a minute.
No worries. Can't even really hear it.
Or a helicopter or something. Sorry about that.
Looking for you.
I tried to, I've got the sound umbrella up, but can't see me. But yeah, I tried to, like, in Melbourne in these early days, just before the summer, it's beautiful weather. So I tried to be outside as much as possible, just in the backyard. Because when the real summer comes, then the temperatures are going to be like 45 degrees Celsius.
Unbearable.
Everything will be on fire and it'll be terrible. So this is the good part. Anyway, so what I was going to say is we kind of have a choice, right? We can do the recursion in this voting round, and that. So instead of taking a token name, this would take a list of token names, and then we could kind of, instead of closing here, we could recurse. So that's perfectly fine. Another thing we could do is we could leave the recursion to the function that calls us here. So instead of, like, obviously we can't just close at the end. Sorry, I guess. Yeah, sorry. So actually, let's take it. Let's take it a couple of steps up. Let me just kind of pause what I was talking about, this recursion, where to put the recursion, and let's go back into single round payout. So right now, this payout closes at the end of the contract, except when we continue it, obviously we're gonna have to actually replace this with the thing that follows, not necessarily a close here.
Yep.
So we could try to jam the recursion in here, but that's gonna be super awkward. Because really we are recursing on those token names outside. So what I'm going to do instead is add another parameter, which is just like what you would call a continuation. So that's going to take another contract and cont, and then instead of closing, it's going to do cont here.
Okay.
So what this means is instead of always closing at the end of a single round payout, we take this contract that is to follow it, right? So what that means is we're going to do a single round payout for one, and then we're going to pass it around the next contract. That's real important because that keeps this thing kind of simple, but not hard coded to only be one thing. So
makes sense. Okay.
So then we have to pass around, pass what's being, so for now, I'll just pass a closed contract in both. So again, we haven't changed any behavior. We've just made something slightly more general, right? So now we've got this issue, right? So we can close or close here, but this is where I go back to what I was talking about is, again, we could recurse in here, but I guess my experience tells me that it's going to be a bit awkward. So I'm just going to do the same trick, right? We're going to pass this continuation through here again.
Okay.
So it takes another contract, which is a continuation.
So in a way, the contract is really looking for another contract until it doesn't get one.
Yeah, eventually you're going to, like, when it bottoms out, when the recursion bottoms out, we're going to get a close.
Gotcha.
But what I'm saying is, like, what I'm really trying to emphasize here is that you don't have to immediately go to recursion. Sometimes it's simpler for these functions to just take another parameter, which is like, I don't know anything about this recursion, but I need you to give me another contract to know how to continue.
Gotcha. And that makes sense. And, honestly, when I asked about using recursion on this, it was just because I don't know other options. So
no.
it's awesome to hear like different ways to do it.
And we will ultimately end up using recursion. I just want to make sure that the recursion is in the right place. Like, it can be tempting to start doing the recursion in here, and you're going to get it, like, you can get it done, right? We'd find a way to do it, but we'd end up with a real complex contract. And I think, like, yeah, I try to, this way we've kind of got reasonable steps. Like, this is a single round payout, which is a single round followed by whatever you pass it next. And then this is, a single payout. And then This is a whole round. Again, we just play around and we do whatever you pass it next. And
Gotcha.
yeah, this close here, right? Let me just get us back to there is a small, oh, what happened? Could not match contract with line 77. Okay, I guess, because now, yeah, I've passed those continuations up. So now we have to do it here again. So we're still doing just one round, but now that choice of a close is here, which is getting us closer to where we actually want to be. So I hope that compiles now. I want to show you one more slight simplification. So at the moment we've got, if the observation is 1, then we do all that.
Mm-hmm.
Then we've got the else part. Else if the observation is 2. Then we've got like the payout part. However, this observation could only possibly be 1 or 2. So like we've got this, if observation is 2, then fine. And then we've got this else part, else close the contract because we don't know what to do. Sorry, here, I guess. And that's completely fine because it's never going to get there. Like, so the choice was 1 or 2. So you went if 1, then do this, if 2, then do this. But what I'm trying to suggest is that you don't actually have to say if 2 because like the choice was either 1 or 2 here. So we had this if part that chose 1. In the else part, the only other possibility is 2.
I gotcha. And that makes sense. I think my way of first building out the thing in Blockly was, just about visually understanding, the steps.
Yeah. So I think, so I think this is fine, this kind of thing. So you don't need to check for this 2. There's a nice symmetry. Like, if 1, do this, if 2, do this. But then there's this, like, what led me to identifying this problem is this else close. And it's like, what are we going to do recursively here? Are we going to continue or are we going to close because something went wrong? Like, I just don't know. And the fact is, logically, this branch shouldn't even exist. So I don't want to deal with it. So that's why I want to delete this. So if
the only other option is 2.
Yeah. So not a big deal, but basically that means that instead of this if here, instead of this whole if here, we just have so now that reads, if value is 1, then we pay non-profit 1, else we pay non-profit 2. Slightly improved, and we don't have to worry about what to do with that close, because that's really that's what was bothering me, right?
Makes sense. It was really just an extra close in the process to deal with.
Yeah. Cool. Now, the other thing I want to, let me see. So the other thing I want to do before we continue is really just deal with these timeouts, because at the moment it's 100 and that's not going to work as we start recursing. So I'm just going to take another timeout, like same thing, just instead of hard coding it, making it a parameter. So that's an integer. I think it's actually a slot. I mean, you can put integer and then see what, like that, and then like that. Same thing, just passing it around. And then the thing that calls voting around can say 100 there. And we should be, so it's saying could not match integer with slot. So yeah, that's actually a slot, not an integer. It still takes the number 100 because it's got internal conversion between integers and slots, but you have to say that it's a type slot because.
Gotcha.
Yeah. Cool. So that should be like identical as before. It's just that now we've got that slot parameterized. So I think we're nearly ready to actually do our recursion, which is what we kind of came here to do. But like, you see how I generalize a bit before even attempting this recursion, because I kind of make anything that's going to vary in each step, I kind of make them parameters.
Yeah, it makes sense. It's definitely, and I really, it helped to understand too. The if choice. How I had just made it more complex than it needed to be.
Yeah. I mean, I didn't see it at first, but what led me to noticing it is not knowing what to do with that final else clause, because like, it shouldn't. It's not possible, but if you give it a choice, then you have to handle that default case, and yeah, it just gives you a little bit of I guess. Okay, so now we are pretty close, but we want to now. This is voting round, and essentially, so that remember that takes a single member name and a continuation contract and a slot. So now we're going to want to basically, instead of a single token name, instead of a single member name, we're going to want to take a list of member names. And this continuation contract kind of isn't going to be relevant because it's just going to do all of them and then end, and slot will work out as we go. So I'll make another function called voting rounds. And this time that's going to take a list of token. Remember, lists are in square brackets. And I guess optimistically, I'm just going to say it's this, right? So it takes a list of token names and returns a contract. So now this is prime candidate for recursion, right? So again, with recursion, we handle the simplest possible case, what's called the base case, which in the case of a list is an empty list. So voting rounds of an empty list is equal to, well, close, right? Because there's nothing left to do. It's a voting rounds with 0 members. So in that case, we close. And now the recursive case. So we're going to use the pattern matching approach, which I think is just that's kind of so standard that I want to start using it rather than head and tail now that we've demonstrated it last time. So we'll call it next member or current member followed by followed by remaining members equals. So that's that. And now, because we've done this voting round, it's actually reasonably easy to get it all going. So what are we going to do about timeouts? Yeah, let's just do the thing first. We'll put timeout 0 and then we'll fix timeouts next step. So what do we want to do? Well, we've got a current member. We want to do a voting round, right? So I'll just start a new line because it's, or maybe not. So we want to do a voting round, pass it a current member, which is, yeah, current member. That's our first element of the list. And then the next thing, it takes a continuation, and that's where we're going to recurse. That's where we're going to do, like, we make a voting round for this member, but then we make the continuation. Like, you start with this member, and then you continue with all the other members. So that means you do voting rounds, the recursive call, with the remaining members.
And I know I'm probably getting ahead of you, but it's making me think about remaining members. Where is it going to look back at that original deposit to decide when to stop looking for remaining members?
Good question. My initial thinking was to when this when this function is called, I intend to pass it the exact number of members that it should get. So I want to do that logic of how many members should be in there based on the deposit, like outside of this function. So we'll do it like in here.
Okay.
That's my current thinking about it.
Okay.
Because I
Thank
think
you.
we can. It would be different if I thought we couldn't, but I think we can. So yeah, we'll do that shortly. Right, so voting round, we give it a current member, and we pass it voting rounds, current members. And so that's took a token name, that's that one. Took the remaining contract, that's that one. It needs a slot, which is a little annoying. I'm just gonna
realistically, the slot would need to be, a good amount of time, and then each time someone voted, it would need to be again,
like a good amount of time. Yeah, I agree. So what I'm gonna do is instead of just taking token names, I'm gonna pass the slot with here too. So for each member, they have a slot by which they have to finish. One thing I keep promising you, but we haven't done yet, is this this possibility of members voting in different orders. And yeah, we won't do that today, but I think maybe the next lesson we should focus exclusively on that, because it's quite interesting, right? Because technically they should all be able to vote, but they shouldn't have to wait for each other.
Exactly. Yeah. That is important. Yeah.
So yeah, that's gonna like exponentially grow the Marlowe graph, and that's fine. So yeah, let's reserve that question for the next, because basically what we are going to end up doing is, like, at the moment we've got, like, in a voting round, we've got sorry, where is it? Here. We've got when the member makes a choice, then do this, right? And so what we're going to do is basically this case is going to have to kind of give us all of the permutations, right? So when any of the members make a choice, then continue with the remainder.
Yes.
So yeah, that's quite interesting. So just for this particular lesson, just because we've got enough to do anyway, I'm not going to do that part, but let's focus on that part next time, because I think I've promised you
That sounds awesome.
like 3 times and we still haven't done it. So the main thing is that you're going to get a combinatorial explosion. So even with like 5 or 6 members, this is basically going to become too big for Blockly, but that's okay. Hopefully it's not big for Blockly for the simulator to run. Anyway, just cool. So that's what we'll do next time.
Yeah, I'm looking forward to it. That'll be awesome.
But this time, so what I've done is, instead of just giving it a token name, I've said, like, it's a list of tuples with token name and slot. So that's basically saying we've got a list of members, and each member has a slot by which they have to vote. Yeah, and so instead of just taking a current member, now it takes a current member and a current slot. And now we can pass in current slot. Yeah. So this should compile, except actually it won't compile because we have to actually.
No, it did.
Oh, it did, because we're not using it, right? So
I think it always excites me and impresses me when, after you've done all these changes, we can still go look at it in Blockly.
yeah, but actually that's just because it's ignoring this, because we're not calling it from this main contract. So it's not quite as good as we were hoping. Okay, so anyway, so what I'll do is I'll just add that parameter to the contract, and I'll say, I don't know, what's this, members and slots, And instead of just doing one voting round, we'll do voting rounds, members and slots. Now it definitely won't compile because we have to actually, when we go here, we have to give it some slots. So I'll just give it like 3. So we can say member 1, slot 100, member 2, slot 200, member 3, slot 300. So now in theory, this should compile and give us what we want. Yeah, send to Blockly, cool. All right, so we got member 1 now. They vote depending on which side gets, depending on which side kind of executes, we either get that one or the other one, which is actually, I'll just get rid of this so we see it. Yeah. Otherwise we get that payment one and that recursion there. So, and then we've got member 2. And let me just, again, if they choose 1, then we do member 3, and yeah, like you see, it gets quite big even with 3 members.
Yeah, I see what you're saying though. In the way that this outputs in Blockly, it literally is creating the workflow for each one or 2. Yeah.
I mean, this goes to show why while in theory you can do it in Blockly, in practice you really can't, right? Because it's like, and like once we do, for it creates this whole tree. So basically we've got we go back to Haskell.
You've got a whole tree for choice 1 and a whole tree for choice 2.
Yeah, so it's kind of quite big and blocky anyway, and this is 8 choices. And now remember that when we do this flow and also every other, so if we do every other combination, so it'll be member 1, member 2, member 3, member 1, member 3, member 2, member 2, member 1, member 3, member 2, member 3, member 1, member 3, member 1, member 2, or like you end up with 6 times what we'll actually have. So yeah, just going through all the combinations here, you'll end up with 48. Keeping in mind that that's for 3. If you do like
10,000 voters,
10,000 voters, then well, yeah, it's gonna be an interesting question of whether, like, I would say at that stage, I'm skeptical that the Marlowe simulator is gonna run it, but Marlowe itself, like the Marlowe simulator that runs like without the web, and presumably the compilation to Plutus should still run, I hope, if this is made to be scalable, which I think it is.
Yeah, I'm sure it could.
Yeah. So
I mean, I don't expect the playground to do it.
Yeah,
but
the playground won't do it. Just because it's so exponential. It's double exponential, right? Because you've got an exponential based on each vote, and then you've got an exponential based on even
their choice.
Like factorial based on the combinations. So just keep that in mind. Anyway, so now we're in a pretty good slot. Now all we have to really do is work out what this should be. There's one more thing I want to do, which is this contract thing should take in a total amount here, rather than just hard coding it. So we'll just give it integer, and that can take a total pool. Would you call this a pool? Yeah.
Campaign.
Oh, total campaign. Okay. Oh, total campaign amount, maybe.
Yep.
And then we want to pass that into just here for now. All right, so nothing's really changed. We've just made it. And then something has changed. We have to now we have to pass it in here. So I think we had 100,000. So one thing you'll notice is that the first time we did a refactoring session, it was mainly for the purposes of readability, but now we're actually doing it for the purposes of being actually able to write this general contract. So our refactoring is driven by needs, not by aesthetics. But those things are we kind of end up getting some aesthetics as a freebie.
Yeah, absolutely. Yeah, this is very much more functionality driven.
Yeah. Yeah. Okay. So now we want to, I guess, do a final thing where basically we calculate based on how many we have. And I'm sorry, there's going to be a little bit of math here. But,
so there's just a reminder, in a vote, a total of 10 is paid out.
Yeah. So let's do that. That's the first thing that we might want to write down somewhere. So total payout per vote, and that's an integer, is equal to 10. Yeah.
Yep.
So then what we basically want to do is write a function that takes a campaign amount, like an integer, like 100,000 in this case, and generates you a list of members which you want to process. So yeah, so basically
or a total number of votes.
Yeah. Well, I guess I wanted to. Yeah, you're going to have a total number of votes in between, but then you need to generate this list of member names and slots from that total number of votes.
Gotcha.
So I was going to kind of skip that step, but we can do it. In fact,
no, that's fine. That makes sense.
The total number of votes will be an intermediate step. However you slice it, you have to be. So I'm going to write a function. I'll call it, I don't know, gen members and slots, gen for generate. And it takes an integer, which is the total campaign amount, and it'll return us this thing that we need, a list of token names and slots. And gen members and slots, and it'll take amount equals. So there are going to be a couple of Haskell-y things that you haven't seen here, but I'll actually open up the REPL and see if I can show you. Like we'll drive it from here, but then I'll kind of jump to the REPL for slightly simpler examples. So there's this thing called let, which kind of lets you have, intermediate variables. So for example, let me just quickly, so that was what we had last time, but like, so for example, I might say let apples equals 1, oranges equals 2, in apples plus oranges. Oh, right. And I can say like total fruits. So yeah, the way this syntax works basically is you've got something called the let, and then you've got a bunch of variables, like in this case, apples is 1 and oranges is 2. And then there's this in, and then a final expression that combines some of those variables that are in there. So if I look at total fruits here, it gives you a 3. So what that does is it just allows us to give smaller parts of the calculation some names so that we can kind of keep things readable. So you'll see why I'm doing this, right? Basically, we'll go let, not lest. Let. So we'll say number of votes equals, I'll call this campaign total. Yeah, campaign amount. So number of votes is equal to campaign amounts over total payout per vote, right? So that's our number. So that means our campaign amount was 10,000, but it can potentially be any number. Total payout per vote is 10. That's probably not going to change, but you want to write these programs in a way that allows you to change it if you were to choose, so
Makes sense.
It's a good thing. So yeah, and then we want to, I guess, return something, and we still aren't there. So for now, I'll just return an empty list, but that's our first shot at this function, right? So we worked out the number of votes and the campaign amount divided by total amount per vote. So that's how you work out the number of votes. Okay. Now, the next thing we're going to have to do is we're going to have to do this, for this number, we're going to have to kind of go number of, we're going to have to kind of go 1, 2, 3, 4, ... up to a number of votes. That's our next
Okay.
next thing that we have to do. So Haskell has I'll just show you in here. There's a syntax for lists. For example, if we go 0.5, that gives you a list of 0, 1, 2, 3, 4, 5. So that means that we can create like if we got, I don't know, let's num votes equals 10, then I can go 1.num votes, and it gives us a list from 1 to 10.
Gotcha.
So that's the first step, right? We have to kind of create one member of the list for that. So let's, I don't know, vote numbers equals 1 ... number of votes. So that's just giving us like, sorry, where am I? That's just giving us like one of those. Now, I'll do two parts for this because this is a new concept, and it's gonna be a concept that we're probably gonna have to come back to. But I'll quickly just I'll show you some examples for it. But it's quite a complex. There's a bit of depth to this, so as long as you have a surface understanding of it, enough for us to complete this function, I'm happy. Like, you don't have to have a complete understanding. So far we've always done recursion when we wanted to do something to a list. It turns out that there are these kind of higher level functions that lets you not do recursion. So there's a specific one that I want to talk about today, which is called map. So what a map does is it takes one of these lists and applies a function to each of these lists, each of these items, and gives you the new list with a new function applied to everyone. So for example, you might want to double each item, right? So you'll go map times 2, and it'll go 2, 4, 6, 8, 10, and so on.
Gotcha.
Okay. So the first,
and you can use map for multiple different purposes, or just for like math?
No, for any function, right? So you can use it for math, which we're going to do to work out the slots. And you can also use it for generated as member names, which is like appending the number to the string member. So it's not to do with math, it's to do with, so we can have like something completely non-mathy. I don't know, apple, pear, banana. And we can, I don't know, map.
You could create like a apple banana milkshake.
All right. Yeah, that's a cool thing. Okay, so sure. So we start with that. Actually, what we're going to start with is that's a great example. Actually, I really like it. So we'll write a function called make milkshake. Okay. So make milkshake is going to take a string and return us a string, and make milkshake flavor equals flavor appended to the string space milkshake. All right, it's stupid, but it's allowed.
No, it helps me. I get it.
Yeah. So now we can say map make milkshake. Sorry. Map make milkshake apple. Oh, hang on. Banana. Vanilla. Chocolate. I don't know about apple.
Yeah, that would be a good milkshake, banana vanilla chocolate.
Yeah, so that
banana
means
chocolate.
we start with banana, vanilla, and chocolate, and the result is banana milkshake, vanilla milkshake, chocolate milkshake, right? So what it's done is it's applied that make milkshake function to each element of the list.
Gotcha.
All right, so let's do slots, because that's the first thing we know. So what I'm going to do is we've got the vote numbers. So let's make slots. Slots is equal to, I guess, well, let's go to, so we want to, for each, I guess, number member, we want to multiply by 1,000, maybe. So that gives us 1,000 steps for each. I'm just going to go with 1,000. Obviously, we're going to have to think about these slot sizes, and when we do that combinatorial thing, then everything's going to change. So I'll call it make slot, and it's going to take an integer and return us a slot. We're going to have a small issue. You've got another 20 minutes to half an hour, don't you?
Oh yeah, no, I appreciate it.
Yeah, we're hitting the hour, and I realized that, yeah, just I want to get through this. So, I mean, basically, so I've just got to make slot. It takes an integer and should return a slot. So I'll give it like n. N is a typical name for a integer, and we'll go n times 1,000. And I think that's going to give me some type errors. So let's just. Okay, well, this is going to give me a type error, but we'll get there. We'll fix it. But now, main thing I wanted to show you is I can say map make slot vote numbers. So what that's going to do is give you like a slot for each of these vote numbers. So let's see. I think it's not going to like that. Yeah, it already doesn't like it. Couldn't match slot with type integer. Ugh. I'm a little bit. What's that whining about? No instance for fractional. Oh.
What's it complaining about? Fractional.
Yeah, I think it's just is it div? I think let me just have a look. Sorry. Okay, I see. Yeah, so so in Haskell, it's got two division operators. One is this, the one that you'll see in other programming languages, which is just like that. Mm-hmm. And there's this other one called div. So div, basically, if you got two integers, then you want to use div. which is like kind of does a division, but it gives you an integer back, which means that it can't be fractional. So for example,
Gotcha.
5 divided by 2 is 2.5, but 5 div 2 is 2, because it just gives you the closest integer and it drops the remainder. So
That makes sense.
because we want an integer ultimately, that's the best we can do. So
Yeah, we don't want a half a vote.
Yeah. So in the case of if these numbers don't line up, you might have a little bit of campaign money left over, which is probably okay. Maybe, I don't know. Like, but
I think they would. I mean, the contract would be designed up front where they always did.
Perfect. So I think that's what that's moaning about. Wow.
Nice.
So okay, cool. So to convert from an integer to a slot, you say you passed in, you just pass that integer to the constructor slot. Constructor is like a function, but starts with a capital letter. It's basically, that's what a slot is. It's like, it's got this label slot and it just takes an integer. So that's why, yeah, cool. Okay, so that's cool. Now we've got slots. Now I want to see them, but we can't quite see them yet because this thing is returning both token names and slots. But yeah, this just has slots. So before we create the token names, I'm going to show you another function called zip. So zip is very simple. It takes 2 lists and it puts them together into one list of tuples. So for example, if we have, let's see, flavors equals banana, chocolate, and vanilla. And then we might have another list, which is like numbers 1, 2, 3. This is all so far. And then there's a function called zip, flavors, numbers, for example. So it takes two lists. It can be of different types. And it kind of zips them together. So it gives you one list of 3 tuples, which is, the first one's banana, the second one is chocolate, the third one is vanilla, and at each of those is 1, 2, and 3.
Gotcha.
So it's kind of zipped together. That's going to be real cool because we're going to we've generated the slots, we'll generate the members, and then we'll zip them together. That's why.
Oh, now I get what you're saying. I'm clicking now.
Yeah, so I'm just going to like right now, just because there's one small bit that we still have to do, but I'll just say members equals, this one I'm hard coding just for the time being. So member 1, member 2, member 3, and then we can return zip. I think actually, yeah, I think it's zip members slots, right? Because we want to return this token name slot. So slots is a list of slots. Members is a list of strings, which is kind of like token names. And then
just a thought, but you've done so much to this already. I feel like you should copy and paste it somewhere else. You never know with.
Yeah, sure. You just, you don't want to lose it, huh?
Yeah, you're using a web-based editor.
Yeah, I get nervous about that, although lately I've been trusting it more and more. But yeah,
you've just made so much progress in it.
Yeah. Oh geez, hang on. Cool, it's here. It's in the file.
Cool.
Cool.
Just makes me feel better seeing all these changes.
Yeah. Cool. So the next thing is, so we've computed the slots properly, and we've just hard coded the members for now. That's our very next thing that we're going to do. And we've zipped them together. I guess like just because the members come first, I'll just put them here first. So we created slots with a map. Cool. So that should the members will just be 1, 2, and 3. more thing we have to do is actually pass it into the contract. So instead of passing these hard-coded members, we'll pass in make members and slots 10,000. And now that we know let, we can also go let total amount equals 10,000 in all of that. And then we can say total amount here and total amount here, so we don't have to repeat ourselves. And one thing I want to show you before we run it also is that if one thing is longer than the other, zip is gonna just zip what it has, right? So it basically is as long as the shorter one. So if we got like 1,100 here, it's still gonna give you, that zip is still gonna give you 3 because that one has 3.
Gotcha. Okay.
Yeah. So that means that here we're gonna get 3, which is good. That's what I wanted. Because we can't generate 10,000 with. Okay, what have we got? Make members of slots. Gen members and slots, sorry. Cool. So that should technically. So main thing I want to look at is those dynamically generated slots, right? So we got when 1,000. So the first one is 1,000, which is what we wanted. Then the second one should be 2,000, and it is.
Nice.
Right. So we've generated that thing. Okay. So now let's generate the names, and then we're done. So you've seen now we're going to use map for this. So just like we said, make slot, we're going to make another make member name. And it'll again take an integer and it'll return a token name. Again, same complaint about token name as I've always had. That should be a role name or something, but yeah. Make member name n is equal to now. I'll just write member for now because I want to do this part. So now, just like we've done a map, make slot to vote numbers, we'll do a map make member name vote numbers. So this is quite elegant now. We get vote numbers, which is a list of 1 to number of votes. We turn them into member names, we turn them into slots, and then we zip them together, and that's our final members and slots that we've got.
Nice.
Anyway, but this, so it's got to return a token name, which I guess is token name. So let me just compile this. It obviously isn't done. Make member name. We've got some errors. Perhaps you want to name data constructor. No, it's good. That help? It's looking promising. That's taking unusually long, isn't it?
It is taking a little while, that's for sure.
What's the error? I don't believe that worked.
Well, it didn't create this in the block layer. I think
Yeah.
it didn't return an error either.
Timed out or something.
What have you changed since the last?
This thing. Okay, I'm gonna do what I've done before, which is gonna be, yeah. So I'm gonna not import all of that because that seems to break it. So we should be back at compile error now. Yeah, we are. Cool. And instead I'll say from string, maybe. From string. So yeah, this thing is called, this is where I go to Google. So it's called isString, which gives us a from string, and that is in data string. Okay, cool. So basically, to get to a token name from a member name, we have to use from string, and from string is import data.string. Yeah, you just import that, and that should
The compiling's taking longer because of the import of the additional resource.
yeah, maybe it just has a kind of, I'll try and, yeah, because did it just like not compile again? Okay, I'll import just from string. So that's pretty minimalistic now.
Still doesn't really like it.
Yeah. I mean, I can return member here. Hang on, let's just get to a place where it works again if we can. Like, I mean, actually, let me just do one thing. Let's have a look at the console, see if it. Yeah, but I'm sure this has a. It's natural for this to have a timeout. Okay, so. Oh. N. Oh, well. Something like that should compile. Because what you can do is this token name is like one of these overloaded strings, which is basically means that Haskell, if it just sees a string, it can convert it to a token name. That's why we've been able to use it like here. But that's only if you use like a hard-coded string like that, not if you construct a string, which is where we're going now. We're going to construct a string, which is member1. And why? What's going on? I feel like something has happened, but I'm not sure. Yeah.
I don't remember. You didn't really make that much.
No, like, okay, let's just. Just comment it out. Just that one token name, which we've already had before. Cool. So now, let's see if this compiles. It does.
There you go.
That's not good. That means I was going to blame, the playground for being down, but like,
you better make the backup now that we got the working.
That's where we were anyway. Let's see. Yeah, that's exactly where we were. So we're fine.
Yeah. Okay.
So let's just try integer to token name, make token name, whatever the parameter is, equals member1, just for now. Okay, so that shouldn't have any problems. Cool, that works. Okay, now we can put an N there and map, make token name, vote numbers. Boon, I know what's happening. That number's too big. So it's trying to generate a huge giant graph and never finishing.
Oh, okay. I got what you're saying. Yeah, put it at
Put it at like,
yeah, 100. That would be 10 votes, 100.
let's go 30. So
Okay.
we stay with our 3-member thing. Yeah.
Yeah, that
And
makes
we'll-
sense.
Yeah. And then we'll increase it because that's, yeah, I think it just goes, oh, this is too much, and it just cuts out. So that's because this doesn't just compile, it actually runs it to generate the thing. So I think it's, yeah, see, now it's fine.
Yep.
So and that's been the problem all along. So I think we can actually pass in that. Yeah, that's kind of where I was going at first before it crapped out. So this should still be okay. Okay,
Nice.
and now, so we're at the so we want to say, member, and we want to add the number n to it. Now this isn't going to compile because you can't add that's n is an integer, and member is like a plus that. Sorry, that's definitely not going to compile. So that's complaining, can't match expected type char with actual type integer. So there's a function called show, which you may remember, which sends us from basically anything that's showable to a string, and an integer is showable. So I believe that should, could not match expected type byte string with type char. Okay. Because that's a byte string, not a. So token name takes a byte string. Okay. Just give me a second. Let me just read that error.
Sorry.
What kind of dog you got?
2 rescue Great Danes.
Oh, wow. Cool. They're big, huh? Yeah.
Yeah, like 120 and 140 pounds.
Wow. Awesome. So it's saying could not match expected type data internal byte string. Okay, we'll say from string instead after all. So
So from string is just not a function present in the playground. Is that my understanding?
it's, yeah, you got to import it. It's available in Playground, but you've got to import it.
Okay.
So it's just it's a Haskell function that just like it's a little bit like basically every time Haskell sees one of these things, like a standalone string, it looks at the type that's expected. And if it expects a string, it just passes that string. But if it expects something else, like a token name, then it tries to call from string on it, which kind of has the effect of converting it from a token name to a from string. And like, there's a little bit more to it. I'm just kind of simplifying it because I don't want to talk about type classes for a while. But yeah. Okay, so now anyway, let's make this, I don't know, 50, like you said, not 500, 50. So because we're basically finished now, right? So we've got members and we're generating this map. Sorry, we're generating a map, make token name. So that's going to go member 1, member 2, member 3, member 4, member 5. Slots is going to make slots, 1,000, 2,000, 3,000, 4,000, 5,000. And then we zip them together. So that's gen members and slots. So we're in a good place, I think. Okay. I think, can we zoom out? Let's look at the big picture because it's a,
Oh yeah, just a tiny little blockly contract.
yeah,
Holy cow.
that's with 5. That's with 5 in a fixed order. Like, and this is the, I mean, this is kind of the limitation of Marlowe, right? And I have to,
Well, you know, but this whole thing was developed from that small contract I
yeah,
sent
that's
you
right.
with.
So we've generalized it and made it, so let's send it to simulator because I mean, it's cool. Okay. So we can start simulation. So we deposit 50 ADA. So choice value 1. So yeah, we can go 1 or 2. Oh no, yeah, 1 or, so we'll say member 1 vote. Okay, we'll just, to make a plan, we'll make non-profit 1 get the first 3 votes and non-profit 2 get the second 2 votes. Yeah.
Sounds good.
Okay, so member 1 votes 1, member 2 votes 1, member 3 votes 1, member 4 votes 2, member 5 votes 2. And now we can look at the results. So these are all the votes that happened. And if we look at the logs, non-profit 2 made 10 ADA, non-profit 1 made 15 ADA, lottery 2 made 5, lottery 1 made 5, and WeThinkItMatters made 15.
Nice.
So I think
it worked. That's awesome.
Yeah. Cool. So there are a few, just to recap, few things. Map is
Save that bad boy.
Yeah. I'll send it to you and I'll upload it to you together with the video. Actually, let me.
Cool beans.
I'm gonna stop.
That was awesome.
How do I stop recording?